Earlier in this chapter, we saw that for series that converged by the integral test, we had a way of bounding our truncation error. Remember, the importance of that is if you're going to feed this to a machine and just tell it to add up the first million terms or billion terms or whatever, you need to know how accurate that sum is. Maybe you don't need a billion terms. Maybe 20 terms is good enough. We have a theorem as well for alternating series. And actually, the theorem is, the error analysis is much easier. So first of all, let's look at what the theorem says, and then I want to just give you sort of a picture of why that's true. So starting off, say we have an alternating series and say it converges by the conditions of AST. So it satisfies those three conditions. And here they're saying, remember, in those conditions, they didn't necessarily need to be true right at the beginning, but eventually. So they're saying, as long as you're past that point, then this remainder theorem here, this truncation error theorem, holds. And what it says is, remember, this was our notation for the difference between a partial sum and the actual sum, right? The actual sum minus the partial sum, actually. So this is the absolute value of our error, and it's less than the next u. So all you have to do is write down what would be the next, without the plus minus, what would be the next thing that I would be summing up. And that would be a bound on your error. So there's really no computation needed. So let's first look at an example and then look at a picture of why this makes sense. So let's just look at something we've seen. Say we have the series -1 to the n plus 1 over n. And say we're going to approximate that by just adding up, 1 minus a half plus a third. Say we're just going to stop there. How good is that? How good is that as an approximation of that sum? Well, what is this? This is S sub 3, right? So remember our notation here. The n represents what order partial sum you're looking at. So for us, the n is 3. And it satisfies the conditions, right? We know that the 1 over n are greater than 0. The 1 over n are non-increasing. And the 1 over n are headed to 0. So we know this series converges by AST, which is what this theorem needs, first of all. So what it says then is that the magnitude of our error, and so the notation R sub 3, and remember what that means is whatever this infinite sum adds up to, the difference between it and this third partial sum that we're using. So again, think of that as the error magnitude. Well, what's the next u? Well, the next term is minus a fourth, right? But we just want the 1 over n part, so just 1 over 4. And that's it. So very easy to use, doesn't really require any computation. You just, whatever that next u would be, that works as an upper bound on your error. So if you think about writing an algorithm, if you wanted to have a machine approximate this with error less than 10 to the negative fifth, well, just tell it to keep adding up terms until it gets to a term that's less than 10 to the negative fifth, and then stop. Because the next term is always a bound on your error magnitude. OK, so let's try and think about why this is true. Why is the error magnitude less than the next term? And what I want to do is just draw an arbitrary series that, not necessarily this one, but one that satisfies the conditions, and draw a picture of what the partial sums need to look like because of that. So I'm going to graph along this axis is going to be n, and along this axis is going to be my partial sum. So let's think about what the partial sums have to look like if you have something that satisfies AST. So think about this again, just in general. Let's think about, we've got U1. So our first partial sum means just add up the first term. So it's just U sub 1. And what do I know about U sub 1? Well, think about our conditions. In general, the terms have to be positive. So that's some positive number. So my first partial sum is some positive number. I'm going to place it nice and high here because I know what's going to happen next. But I know it's a positive number. What about my second partial sum? Well, it's U1 minus U2, right? It's an alternating series. So the next thing is going to subtract. But because the conditions are satisfied, that really is a positive number, right? All the U's are positive, so I really am subtracting. I really am making it less. So the next partial sum has to be something smaller than the first partial sum. But these guys are also decreasing. Non-increasing, but just for the sake of the picture, let's say they are strictly decreasing. I guess non-increasing is fine, but they eventually have to head to 0. But the key is I'm not going to subtract away more than I just added in, right? So that next partial sum is going to be less, but I won't go negative, right? I won't go below this axis because U2 is not as big as U1. It might be the same. I guess I could be right on the axis, but more than likely it's less. And then so on, right? Then the next one, next we're going to add. So now we're going to head back up. But U3 is less than U2. So I'm not going to make it up as high as I was before. Because think about it. How far did we jump down? We jumped down U2. Now we're jumping back up by U3, but it's less, right? Let's just assume strictly less than. Say U1 is less than U2 is less than U3. Then every time I make a jump in these partial sums, I'm jumping the other direction, but I'm not going to go as far as I went before. So the next partial sum, in general, I don't know where it is, but it has to be less than this one because at this point I'm doing S sub 4. Subtract, then add, subtract, then add, but never jumping as high or low as you were before. But we know this converges, right? The whole assumption is that you're dealing with a convergent series. So somewhere in here has to be the actual sum. So what happens is each time we jump, we jump, and we have to jump over the line. Think about it. How do I know these dots are all above the line and these are all below? Well, imagine from S6 to S7, imagine I didn't jump over the line. Say I jumped to right here. Well, I just got done arguing that you'll never be up that high ever again. Well, how am I going to converge on this line if I'm never up this high again? I would only go down from there. So every time I jump up, I have to be above the line then, because next I'm going to go down and I'll be below the line. So it's always above, below, above, below, above, below. So because of that, what does that mean about our error each time? Well, let's think about this. Let's draw a picture of the error. Say this one. Say you stopped at S sub 4. Your error is the distance from your partial sum to your actual sum, right? This is S sub 4, my fourth partial sum. How far is it from the actual sum? That's what we're defining to be the magnitude of our error, right? So that's, well, I just got done saying that you have to always jump over the line, and that's the key. Because how far is it, how far am I about to jump? Well, that's my next U. To go from my fourth partial sum to my fifth partial sum, I'm going to move a distance of U5. All right, think about this. U1 minus u2 plus u3 minus u4 plus u5. So there was the fourth partial sum. But then to get to the fifth partial sum, I'm jumping a distance of u5. So every time you stop your sum distance from that line, the distance you're about to jump is even bigger. And that's what the theorem says. It says that, well, right here, yes, that the error is always less than the u. In my picture, think of it as the distance you are from that line is always less than the distance you're about to jump, because you're always jumping over the line because of the behavior of being positive, decreasing, and headed to 0. This actually tells us another thing as well. Besides knowing that our error is less than, we also know what kind of error we have. Wherever I stop, like say I stop at the fourth one, if the last thing I did was subtract, I know I'm currently underestimating. If I stop here, where the last thing I did was add, I'm overestimating. Underestimating, overestimating, underestimating. So if we look at this example, not only do I know my error is less than a quarter, I know that I'm currently overestimating, because we currently have jumped over the line, right? 1 is an overestimate. 1 minus a half is an underestimate. 1 minus a half plus a third is an overestimate. So just by looking at the sign there that I currently have just added, I know I've currently jumped over the actual sum, and I'm overestimating. So that's a nice thing. Not only do you get an error magnitude bound, you also know whether you're currently over or underestimating. And that might be important. If you may, for your purposes, want to be conservative and always overestimate, just depending on the scenario. So this is not a proof per se, but I think the picture helps see why that's true. Those conditions will always generate partial sums that do this. They jump over the actual sum, and they keep getting closer and closer to it. So that always causes your error to be less than the next u, or the next distance you're about to jump.